So, welcome to Programming Assignment, Part 2. So here I'll talk about evaluating classifiers. So in the first part, I talked about KNN, which is a classifier method. It takes the data, and then it finds the nearest example that it knows how to label, and then it predicts that. So that's a method of classifying. Here I'll talk about how, given a classifier, we can evaluate its performance. So I'll start off with held out datasets. So let's say we have a dataset. Again, we're talking about our image dataset. So we have like crackly drawn 9, another crackly drawn 9. Let's actually set 9. I'm just going to draw a bunch of numbers. Okay, so let's say these are the images in our dataset, and we have labels for all of these, right? So we have a label here. These are the labels, the actual ground truth labels done by people that looked at these images and decided what they were. So let's say a human's able to clearly figure out that this is a 3, this is clearly a 9, this is clearly a 2. And now what we want to do is, the general idea here is we'll take some of the data, we'll train our algorithm on that, we'll have it predict other data, and we'll check, we'll compare its predictions to the ground truth, which is what the person labeled these as, right? So let's say, we label some of them test, test, test. So what we'll do is we'll train the algorithm. So remember, KNN, you have the training set and the test set. So we'll train the algorithm on everything but test. So this is train, 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 train. And we'll make predictions about these test images. So let's say there's another image. I don't know, let's say there's another image that looks like this. That's like this, right? So let's say a person can tell that this is clearly a 2. This should be the ground truth label for this is a 2, but the algorithm might not be able to tell, right? So the algorithm will train on all the cases that are not test, and then it'll make predictions about tests. So let's say the algorithm sees this example is very close to these 2 examples. So let's say we're running 2NN, right? 2NN, a special case of KNN, it'll find the closest examples. So in this case, let's say these are the closest to this one it wants to predict on. It'll see that the labels for these 2 examples are 2. So the most commonly occurring label of the 2 closest examples is 2. So let's say this is 2. The algorithm would predict 2 for this case. Let's say it predicts this to be 9. And let's say for this case, the algorithm, let's say this is also a test case. The algorithm incorrectly predicts it to be a 3. And for this case, let's say it's correct. So the algorithm predicts what the actual label is for all of these cases except for this case. So in this case, let's count our total data set size is 3, 3, 3, 9, 10. Our total data set size, so n, equals 10, right? This is the size of our data set, the number of examples. There are this is trained, so 1, 2, 3, 4. 4 held out data points. And this is the size of the size of the test set. Test set size equals 4 held out data points. And let's say the training set size is 6. So 6 plus 4 is 10. So the training set and the test set have to partition the data. In this case, we're just assuming that you want to use all your labels. So the accuracy here, so first you have accuracy, then you have error. So the accuracy is the proportion you get right. So here, there was 1 wrong out of 4 that were predicted. 3 of them were right out of 4. So accuracy, the accuracy on this data set, we don't know if this is the actual accuracy if we were to generate lots of these examples, but the accuracy on this data set is 3 out of 4. And the error, so the error in this case for classification, we're just saying this is one error measure. There are lots of error measures, but it's just the proportion you get wrong. So in this case, we got 1 wrong. We predicted 3, and it should actually have been 2. And we got the others right. So we got 1/4 of them wrong. So in this assignment, you're interested in calculating the error. In other cases, you might be interested in accuracy or some other measure of error. There are lots of measures there. So, okay, so that's a held out data set. You have a train split, you have a test split, you train on some part of the data. Usually this training set size is like 70% of the data, sometimes it's 90%, and the test set size is 10% or 30%, depending on what the training set size is. It's the remainder. So usually you want to make the training set size big, because for most algorithms, especially KN, as you get more data, your accuracy improves. So you don't want to waste any data. If you only use like 10% of your data set to train, then your accuracy would be much lower than if you use the entire data set, or like 90% of your data set. So that's why we want the train set to be as big as possible. But we also want a big test set, because if our test set is only 4 data points, we don't really have a good idea what the error is, right? Because 4 data points, the variance on this error could be like plus or minus 1/4. We have no idea what the error is. Based on these 4, I mean, you remember from like, this is actually binomial distribution. You can forget about why, but let's say it's a binomial distribution and standard deviation is going to be pretty high. So we want a lot of data points to evaluate on. We want the test set size to be large because we want to get a good estimate of the error. So we want both of these to be large, and there's a problem there. So one method of getting this is called cross-validation. So cross-validation, in cross-validation, you have your examples. Let's say our images. I'm going to make 10. 2, 4, 6, 8. 4, 6, 8, 10. And let's say the actual labels for these. So green is going to be the actual label. The actual label is, let's say this is 0, so it's 0. This is a 9, so 4. So 4. 2, 2, 0. Okay, and let's say this is 2. This is just a crappy drawing of these. So somebody wrote this on like an envelope, and these are pictures, right? So 9, 9, and crappy drawing of 0. Okay, so let's say this is our data set. So we have these pictures, we have the actual number that a person thinks these pictures represent. And let's say it's clear that this is clearly a 9, and this is clearly a 9 according to a human, but a computer might not be so sure, right? So remember, train test split. In the train test split case, let's say we're doing 90-10 split. Or actually, let's do 70-30. So 70-30 split would say we randomly choose a test set. 70-30 means 30% are tests. So in this case, that would be 3 out of 10. So let's say these are the test cases. This is test, this is test, this is test. We would use these as our train cases. We would take our algorithm. We would say these are the train cases. These are the ones we know the labels for. And we're making predictions about the labels for these ones that we don't know the labels for. So let's say the algorithm predicts this is a 2, this is a 1, this is a 0. So it gets 1 out of, the error here would be 2 out of 3. We got 2 out of 3 wrong. So in cross-validation, let's say to make this nice, let's say we were doing, let's give 0. Let's do 1. Okay. So 0 and 2. So let's say we have a little bit more data. So the numbers divide nicely. So if we were doing 4-fold cross-validation, 4-fold cross-validation, what we would do is we'd have lots of train test splits. So the way we do this is we split the data. First thing we do is we split the data into 4 groups, right? So these are going to be the different test sets. So we're going to have 4 different test sets, and remember the training set in this case is just going to be whatever examples are not in the test set. So let's say this is like test 1. We're randomly choosing. So since we're splitting it into 4 parts, 3 times 4, there are 12 examples. So 3 times 4 is 12. So in each test set, there are going to be 3 examples. So 3 examples per test set. 4 test sets is going to be 12 examples. So that's why I chose 12. So let's say test set 1 is going to be this. So in the first case of the train test split, we're going to train on these, the ones that are not in the test set here, and we're going to test on test one, test one, test one. And then we'll get an error measure, and that will give us one error measure. So let's say we have another test set, test 2. This is the second and test 2. Remember, we're randomly choosing where these test 1s and 2s are among our examples, among our labeled images. So we're coming up with a partition. Let's just do all of these. Test 3, test 3, test 3. So what have we done here? We're going to, since we partitioned it into 4 parts, we get 4 train test splits. And we get to evaluate the accuracy of our algorithm using a held out data set 4 times. So for test 1, we get some error. Let's say for test 1, we make predictions and we get a third of them right. So let's say accuracy 1. Let's be concrete. Let's say the predictions were 1, 9, 4. So the algorithm predicted 194. It's actually 094. So accuracy 1, accuracy for split 1 for the first training set, which consists of the examples that are not in the first test set, because training and test set add up to all the examples. So the accuracy 1 is going to be, error 1. We care about error. Accuracy and error are just one minus the other. So error 1 is going to be 1 out of 3. There are 3 test examples. 1 out of 3 was wrong, so the error that we're using here is just 1 out of 3. And this is just 2/3, 1 minus 2/3. So error 2. So let's say we have another trial where we have a different split. In this split, we train on everything but test 2, test 2, test 2. So let's say, in this case, so test 2, let's say we make predictions 2, 0, where's the other test 2, and 0. So our algorithm is completely right. So in this case, error 2 is going to be 0. There are no errors. 0 out of these 3 examples are wrong, right? And we do the same. So we're rerunning our algorithm 4 times on different train test splits. And let's say we do the same for error 3. Let's say we get 2/3, so a lot of examples wrong. And then error 4 is 1/3. Right? So what we've done, let's say we notice when we've done this, we've chosen a particular algorithm. We've chosen some algorithm for making predictions. We want to evaluate. We want an estimate of the held out error. So if we were to train on 9 out of these 12 examples, or if we were to train on 9 examples in general, what would we expect our error to be? So this is a lot better than the original train test split, because the original train test split would only have one of these cases. We would just get one number. Here we get a bunch of numbers, so we can average them. Remember central limit theorem and law of large numbers. If we average a bunch of independent samples, which these are not exactly independent, that's a separate discussion, then we get something that's a better estimate. The variance goes down. So in this case, if we average these, so sum them up divided by 4. So this is 1 plus 2 plus 1 divided by 12. Oh, that's convenient, right? So I'm just dividing this 1/4. Actually, I'll write this out. This is 1/4 times 1/3 plus 0 plus 2/3 plus 1/3. So our average error across these is going to be, bring out the 1/3, and then it's just 4 over 12, and this is just 1/3. So our average error is 1/3, which makes sense if you distribute it. So this is this cross-validation method gives us a better estimate of our error. So that's why we're running cross-validation. So what you're doing in this assignment is you're given this cross-validation, the number of splits in your cross-validation method. So you're given, this is M. So what you need to do is split the data into parts, and then feed it into this magical predictor. So this magical predictor, what it'll do, it won't just predict, it'll evaluate, it'll give you this error. So let's go back to this. So you give this KNN script, you give it a K. So let's say you give it a K of 2. We were talking about 2 and N. So it takes the 2 nearest examples, and then it takes the most commonly occurring among those. And in a tie, let's say it randomly picks 1 or something. I don't know exactly what it's doing, doesn't matter. And let's say this is let's say digits.txt, which I talked about last time. So let's say you split up digits.txt into just digits files. So just digits files consisting of the digits in the test set. So in this case, test data would look like the numbers for this picture, the numbers for this picture, and the numbers for this picture. So the test data lines, there will be 3 lines, and each of them is a picture. Notice the length of these lines, the number of elements in these lines, is going to be 784, not 785. 784, remember, is 28 times 28. That's the number of pixels in these images, right? The test labels are just going to be 0. It's going to be a file with 3 numbers in them, 0, 9, and 4, right? So 0, 9, 4. The train labels are going to be 2, 0, 4. There are lots of these, right? 2, 0, 4, etc., etc. So let's say 2, 0. They're going to be 1 for each line. 2, 0, 4. Dot, dot. And the training data is going to be so there are going to be 9 lines here. And there are going to be 9 lines in the training data. So and there are 9 of these. 9. There are 3 here. There are 9 labels. 3 here. So this script here is given the file names, and you have to create these files yourself. So you have to take your digits.py file, which has it has the pictures plus the label at the end. You have to convert it to these different training and test splits, and then plug it into this. So what does this method do? It takes this training data, it makes predictions on the test data, and then it returns the error, like the deviation from the actual labels. So in this case, for this particular case here, it would return 1/3, which is error 1, which is the error on the first split. And you have to try this for different algorithms. Each k gives a different method of predicting, right? So if you try k equals 3, you might get higher or lower accuracy or higher or lower error, depending on whether that method is better or not. And so since cross-validation gives you a better way of evaluating classifiers, gives a pretty good way of evaluating classifiers, you can try different k's, and if you average over all of the splits for that particular k, you should have an idea of whether one k is better than another k. So this is called like hyperparameter tuning or just parameter tuning. And you don't need to care about the words, vocabulary, or whatever, but that's what it's called if you're interested. Okay, so we have this script. Given your m, if your m were 4, you'd split it into 4 of these. So this is one case, this is one split. You'd have another split, 4 of them total. And then for each of these, you'd get a number. For each k, remember you run over all case. And so what you get is you get a 2D matrix, which is the case, all the k's you run it for, by which split number it is. Right? So different split numbers, different k's, and you get different values. So let's see what this matrix looks like. The matrix is going to look like this. So in your assignment, you're given k values. I think there were 2, k equals 2, 3. I don't know. I'm just going to make stuff up. I don't know if these are exactly the values. I think there were 5. So you want to try for k equals for 2nn, 3nn, so 5 nearest neighbors, 9 nearest neighbors, 11 nearest neighbors. These are each different algorithms and methods of predicting. You want to create different data sets, different train test splits. Let's say split 1. Split 1 would correspond, let's say in this case, to the test 1 data set. Split 2. And this is, of course, if you were given m equals 4. If you were given m equals 6, you'd split it into 6 parts, 6 evenly partitioned parts. Split 3, split 4, right? And for each of these, what do you do? This box here is the error output by split 1. So split 1, remember, you're going to, based on the split, you can generate the test data, the test labels, the train data, the train labels. You can plug it in here. So for this split, you're creating these. You're creating these files, and then you just give the names of the files to this program. You give k equals 2, and then you run it. It'll give a number, and you stick this number here. Let's say it's 0.04 error. Right? And let's say for this case, k equals 3. we would plug in k equals 3. In this case, it's the same data here, the same split. So we can just change this one parameter, keep the same file names, and run it again. So that'd be like 0.05. Da-da-da. And you do this for all of these cases, and then at the end, you get average. So remember, the whole point of running on multiple splits is so we can get a more robust measure, a more accurate measure of the held out error, right? Because we're running on like multiple trials, we're getting the error from multiple trials, and if you average them, central limit theorem, any of these theorems, like you converge, the variance approaches 0. So this is 4 cases. So the average, let's say the average is 0.0392. I don't know. So the average is just going to be the average over this column of all of the splits. And this is easy to compute, this last line. So that's why they say this is like m plus 1. This is 4 plus 1, 1 for the average. And this is overall in this case. So that's the assignment. That's it. And you just take this results. You can just run this by hand. You don't need to write a script to magically generate this. You can just like split the data by hand and just run, because we made it so it's like m is 6 or and k is 5. It's just 30 cases. So just run this script for 30 times for different values, get all these numbers, just put them in a table, and feed it into the, just return this table. So you don't actually need to write a script to generate this. You can just generate it by hand.